My friends, I'm not just going to compare heat and work, but later in the video, I've got something that might just blow your mind. At least it blew my mind the first time I learned about it. So let's get into it. Well, work, very simply, is an applied force causing motion. So if we apply a force on something, cause it to move, then work is being done. You may also know work as force times distance, or more precisely, displacement. And the main equation for work is this right here. Now, if you're not used to this notation, don't worry about it. You can skip over it. But it's the dot product between the vector force, the force vector, and the displacement vector. And there's an integral sign here because we're summing up the force as it's applied throughout the whole displacement. You can also think of work as the change in kinetic energy of an object or the system, according to the work energy theorem. So work equals change in kinetic energy, just like this. And what is work? Well, if we imagine a car that's moving, it's moving, so it has kinetic energy. It doesn't have work. Okay? Same thing with a car that's not moving. If it's not moving according to us, it doesn't have any kinetic energy, and it also doesn't have work. But when the moving car slams into the stationary car, then work is being done during the collision. When energy is being transferred, when the stationary car starts speeding up, and the moving car starts slowing down, work is being done. But after the collision, there is no work. There's many different types of work. If you're in thermodynamics, you're used to mostly expansion and compression work, where we have usually atmospheric pressure or some pressure that's expanding or compressing a gas. There's also work being done due to a spring. And as this mass bobs up and down, there's two different forces. There's the force due to gravity and the force due to the spring. The spring is doing work on the mass as it tries to pull it up in this instant. And gravity is performing work on the mass as it tries to pull it down. There's also electrical work and many, many different types of work. Heat is a different beast in itself. In one definition, it's the transfer of energy due to the absorption of electromagnetic radiation. So this candle might warm up our skin because our skin is absorbing electromagnetic radiation, making it hotter. Another part of heat, which is more commonly seen in textbooks, is the transfer of energy due to a temperature difference. So we have a hotter body increasing the temperature of a cooler body by making those molecules move faster. If they're touching, it's called conduction, and that's heat right there. You can also think of heat as the mixing of fluids at different temperatures. This is called convection. And if we look at this at a microscopic level, we have these faster moving molecules slamming into the colder, slower moving molecules, making them move faster and increasing their temperature. Here we have conduction, and we have heat transfer from the left to the right as the colder body starts increasing temperature. But if we look at this at a very microscopic level to see what is actually going on during heat transfer, we have a bunch of molecules. In order for the slower moving molecules to get hotter, we need a collision to occur. We need the faster moving molecule, the red one, to move and slam into the colder one. And during that collision, work is being done. So in order for heat transfer to occur, work has to be done with every collision. So with every collision, that involves work. As such, heat is a macroscopic manifestation of work. And this is what blew my mind when I first learned this. I just thought this was totally crazy. If we compare the two of them with heat, say we have energy coming in, it could be energy coming out as well. That results in random motion of molecules in our system, whereas work results in an orderly motion. Now, work could result in increasing the temperature, which would be an increase in this disorderly kinetic translational motion of the molecules, but just work itself on its own is due to orderly motion. And if you've heard about entropy before, work by itself doesn't change the entropy of the system, where heat does change the entropy of the system. The key thing about heat and work is that they are forms of energy transfer, how it is transferred. Let's say we have some initial energy state, some final energy state. The transfer of energy is due to heat or work. It's not the energy itself. The energy itself can be like kinetic energy with translational, rotational, vibrational. It could be a form of potential energy, which could be also electric, magnetic, gravitational. There's many different types of energy. But heat or work just describes how that energy is being transferred. The energy itself is not heat or work. Okay, so to summarize the two of them, heat and work both describe how energy is being transferred. They are not a type of energy themselves, and as such, they are not properties of the system. Heat occurs when you have a temperature difference between bodies, also due to the absorption or emission of radiation can result in heat, whereas work, very simply, is moving an opposing force. Now, this is a very simple statement, and I have derivations of equations and calculations and exam problems that go on this, but it's really nice to have a good conceptual understanding of what's going on. Now, on a molecular level, heat results in random motion of the molecules, although work is done with every collision. And with work, that results in orderly motion of the molecules. All right, as you continue on this playlist, we're going to go deeper into heat and work. We're going to get into the laws of thermodynamics and many calculations and derivations, but it's extremely important to have a very strong understanding of these concepts, heat and work, and many other concepts as well. I dive deep into it. Hang in there. You can survive. Cheers.